All right, let's get right into it. Today, we're going to the absolute core of artificial intelligence. We're going to break down the single most important building block of any neural network you can think of, the single neuron.
You know, we hear about AI all the time. It's creating art, it's driving cars, it's doing all this incredible stuff. But have you ever really stopped and asked yourself, how does it actually work? How does it think? Well, believe it or not, the answer to that huge question starts with something incredibly small. It's not magic, it's not some unknowable force. It all comes down to one simple computational unit that's the foundation for everything. So let's dive in.
First up, we need to understand the blueprint. What exactly is this thing we call a neuron?
Okay, so what is an artificial neuron, really? I mean, we're obviously not talking about the squishy biological ones in our brains. So what are we talking about here? Honestly, the best way to think about it is like a single Lego block. One block by itself? Kind of boring, right? It doesn't do much. But when you start connecting hundreds, thousands, or even billions of them together, you can build anything. That's exactly the idea behind a neural network. And each one of these little Lego blocks has just three basic jobs. That's it. First, it takes in some information. We call those inputs. Second, it does one simple calculation on them. And third, it spits out the result as its output. Receive, calculate, generate. Simple as that. Okay, so let's get to the fun part, the core calculation. What is a neuron actually doing with all those inputs? Right, this is the next logical question. We get that it takes in data and sends out a result, but what's happening in that middle step? What's the actual math that makes this whole thing go? The whole calculation really just boils down to three key ingredients. First, you've got your inputs, which we call X. This is your data. Could be anything, like the age of a person or the color of a pixel. Second, and this is the really important part, you have weights, or W. Every single input gets its own weight, which is just a number that tells the neuron how important that input is. And finally, you have a bias, B. Think of the bias as just a final little nudge to tweak the result up or down. And here is how it all comes together. The neuron takes each input, multiplies it by its special weight, and then it adds all of those results together. At the very end, it just adds on that bias. All of that gives it one single number as the output, which we're calling Z. So at the end of the day, a neuron is just doing a weighted sum of its inputs with a little adjustment at the end. Now, that formula works great for a couple of inputs, but modern AI isn't dealing with a couple of inputs, it's dealing with millions. And for that, we need a new way of speaking, the language of scale. And this is a question that anyone who's ever worked with databases will totally get. Doing things one by one is just painfully slow. When you're dealing with huge amounts of data, you've got to find a way to do things in big, efficient batches. The solution is to group our numbers together. Instead of dealing with individual inputs and weights one at a time, we bundle them into vectors. A vector is basically just a list of numbers, kind of like a single column in a database table. So we have one vector for all our inputs X and another vector for all our weights W. And by organizing our data this way, that big long formula we saw before, it collapses into this. This is so much cleaner, right? This is matrix notation. And it represents the exact same multiply and add operation, but it lets computers do it for millions of values all at once, in a single blast. So why do we even care about this? Why does making the math look pretty matter? Well, it's not about looks. It is all about raw, unfiltered speed. And it's what makes modern AI even possible. Now you might be thinking, look, my computer is fast. Why can't I just write a simple programming loop to go through and multiply everything one by one? That's a great question, and the answer is actually pretty staggering. So on the left here, you see a normal loop in Python. It's going through each item, one at a time. On the right, you see one single command using a library called numpy. This is a vectorized operation, using that powerful matrix math we just talked about. It might look simpler, but the real magic is just how fast it is. So what's the difference? Well, to run this calculation on a whole bunch of numbers, the standard Python loop takes 2.06 seconds. Now, that might not sound like a lot, but you have to remember, in a real AI model, this one calculation could happen billions of times. Okay, now what about the vectorized version using numpy? It takes just 20.8 milliseconds. That is not a small difference. That is nearly 100 times faster. This right here is why matrix math is everything.
Without this insane level of efficiency, training the AI models we all use every day would be practically impossible.
All right, let's wrap this up with a quick summary of the key takeaways here.
First, a neuron is just a simple building block, like a Lego. It takes stuff in, does a calculation, and sends stuff out. Second, weights and biases are how the neuron learns which inputs are the most important. Third, matrix notation is the super efficient language we use to handle these calculations at a massive scale. And finally, using vectorized code like you find in NumPy isn't just a good idea, it's absolutely essential for performance.
Hey, if this breakdown helped things click for you, do us a huge favor and hit that like button and subscribe for more. We love breaking down these complex topics. And that leaves us with one final, pretty mind-bending question. We've seen that one single neuron is actually super simple. So, what happens when you connect billions of them together? What kind of intelligence, what kind of crazy complexity can emerge from that? We'll get into that next time.